Imagine holding a photograph of your family, but you can only see the empty space between them. The people themselves are invisible. You know they're there because you can see their effects: the indentation on the couch where someone sits, the coffee cup hovering in midair, shadows cast by bodies you cannot perceive. This is our universe. Everything you've ever seen, every star, every galaxy, every nebula captured by our most powerful telescopes represents less than 15% of what's actually out there. The rest? It's made of something that doesn't emit light, doesn't absorb light, and doesn't interact with electromagnetic radiation in any way we can directly measure. Yet it shapes everything. It holds galaxies together. It bends the fabric of space itself. Without it, you wouldn't exist. Without it, galaxies would tear themselves apart, stars would never form, and the cosmic web that structures our entire universe would collapse into chaos. We call it dark matter, but that name barely scratches the surface of how strange, how pervasive, and how fundamentally important this invisible substance really is. Today, we journey through evidence that challenges everything we thought we knew about the composition of reality itself. Prepare yourselves. We begin.
If you're enjoying the video, feel free to tap that like button. It shows me this content sparks something in you. And if you'd like to stay close as new stories appear, subscribe to the channel. It genuinely means a lot and helps this place grow in the right direction. Thank you for being here.
In 1933, a Swiss astronomer named Fritz Zwicky pointed the telescope at Mount Wilson Observatory toward the Coma Cluster, a massive collection of over 1,000 galaxies located 320 million light-years from Earth. What he was about to discover would haunt physics for nearly a century. Zwicky was measuring the velocities of galaxies within the cluster, watching how fast they moved relative to each other. He applied a straightforward calculation, one that Newton himself would have recognized. Measure the mass of the cluster based on the visible galaxies, then determine if the gravitational pull was sufficient to keep these galaxies bound together. The numbers didn't work. The galaxies were moving far too fast. At the speed Zwicky measured, they should have been flung out of the cluster long ago, scattered across the cosmos like stones from a broken slingshot. Yet there they were, orbiting together in gravitational harmony. To explain what he was seeing, Zwicky calculated that the Coma cluster needed to be 400 times more massive than what was visible. 400 times more massive. Zwicky proposed something radical. There must be dunkel materie, dark matter, invisible mass filling the cluster, providing the gravitational glue holding everything together. The astronomical community largely dismissed his findings. How could 99.75% of a galaxy cluster be invisible? The idea seemed absurd, a mathematical error, an observational mistake. But Zwicky's observations were correct. For decades, dark matter remained a curiosity, an unexplained anomaly that most astronomers preferred to ignore. Then, in the 1970s, a young astronomer named Vera Rubin began studying something closer to home: the rotation of spiral galaxies. When you watch a spinning carousel, the horses on the outside move faster than those near the center. They have to cover more distance in the same amount of time. Our solar system works the same way. Mercury screams around the sun at 47 kilometers per second, while Neptune, 30 times farther out, plods along at just 5 kilometers per second. This is how gravity works. The farther you are from the source of gravitational pull, the slower you should orbit. Vera Rubin expected to see the same pattern in spiral galaxies. Stars near the galactic center should orbit quickly, while stars in the outer regions should move much more slowly. She pointed her telescope at galaxy after galaxy, meticulously measuring the rotation speeds of stars at various distances from each galactic core. What she found made no sense. The stars at the edge of galaxies were moving just as fast as stars near the center. In some cases, they were moving even faster. According to Newton's laws, according to everything we understood about gravity, these outer stars should have been flung into intergalactic space billions of years ago, but they weren't. Rubin had discovered rotation curves that remained flat across entire galaxies, defying every prediction of gravitational physics. She calculated the mass required to explain these rotation speeds. The results were staggering. Galaxies must contain 5 to 10 times more mass than we can see. And this invisible mass wasn't concentrated in the galactic core. It extended far beyond the visible edges, forming vast spherical halos around each galaxy. The evidence was undeniable. Zwicky's dark matter wasn't an anomaly in one distant cluster, it was everywhere. But what was it? Astronomers searched for conventional explanations. Perhaps dark matter was simply ordinary matter that didn't emit light. Dead stars, black holes, cold gas clouds, brown dwarfs, planets floating between the stars. They called these objects machos, massive, compact halo objects. Throughout the 1990s, astronomers conducted extensive surveys, watching for the telltale signs of machos passing in front of distant stars. When a massive object passes between us and a star, its gravity bends the starlight, causing the star to temporarily brighten, a phenomenon called gravitational microlensing. They found some machos, but nowhere near enough. Ordinary matter, even dark and cold, could account for only a small fraction of the missing mass. Dark matter, whatever it was, had to be something truly exotic, something that had never been directly detected in any laboratory on Earth, something that represented a fundamental component of reality that physics had completely overlooked. But the evidence forces us to confront an uncomfortable possibility. We are made of the universe's minority constituent, living in a cosmos dominated by something we cannot see, cannot touch, and do not understand. If dark matter truly exists as an invisible substance pervading the universe, it should leave signatures, fingerprints in the cosmic structure that only its presence could create. Scientists discovered the first signature in the most violent events in the universe, galaxy cluster collisions. In 2006, NASA's Chandra X-ray Observatory captured images of the Bullet Cluster, two galaxy clusters that had slammed into each other at millions of kilometers per hour. The collision occurred 3.8 billion years ago, and the aftermath revealed something extraordinary. When the clusters collided, their ordinary matter, primarily hot gas glowing in X-rays, interacted and slowed down, creating a shock wave of superheated plasma between the clusters. You can see this glowing cloud in X-ray images, marking where the visible matter piled up during the collision. But gravitational lensing revealed something else entirely. Astronomers mapped the gravitational fields by observing how light from background galaxies was bent and distorted. The gravitational center, the location of most of the mass, wasn't where the hot gas was. It had passed right through the collision point, separating from the ordinary matter by more than 3 million light-years. This is the signature of dark matter. While ordinary matter interacts, collides, and slows down through electromagnetic forces, dark matter passes through everything like a ghost through walls. It's collisionless, interacting only through gravity. The Bullet Cluster represents just one piece of a much larger puzzle. Scientists have now observed dozens of colliding clusters, and every single one tells the same story. The gravitational mass center separates from the visible matter during collisions. But perhaps the most compelling evidence comes from something called baryon acoustic oscillations, pressure waves that rippled through the early universe. In the first 380,000 years after the Big Bang, the universe was a hot, dense plasma. Ordinary matter, protons, neutrons, electrons, everything that would eventually form stars and planets and people, was coupled to photons, creating a fluid that could transmit pressure waves like sound waves through water. Dark matter, unable to interact with photons, remained unaffected by these oscillations. When the universe cooled enough for atoms to form, the pressure waves froze into the distribution of matter, creating a characteristic pattern of galaxy clustering with a specific scale, approximately 500 million light-years. Astronomers have measured this pattern in the distribution of galaxies across billions of light-years of space, and it matches theoretical predictions with stunning precision. Here's what makes this evidence so powerful. The pattern we observe requires dark matter to have existed in the early universe at a ratio of approximately 5:1 compared to ordinary matter. 5 parts dark matter, 1 part ordinary matter. This ratio determines the amplitude and wavelength of the acoustic oscillations, and any significant deviation would create a completely different pattern in galaxy distribution. We observe the predicted pattern. The ratio holds. The evidence converges from completely independent measurements made across vastly different scales and cosmic epochs. But this represents just one piece of a much larger puzzle hidden in the oldest light in the universe, the cosmic microwave background. The cosmic microwave background, the CMB, is the afterglow of the Big Bang, light that has been traveling through space for 13.8 billion years. This light carries within it a detailed snapshot of the universe when it was just 380,000 years old, encoding information about every component of cosmic composition. When the European Space Agency's Planck satellite mapped the CMB with unprecedented precision, it measured tiny temperature fluctuations, variations of just a few millionths of a degree. These fluctuations represent the seeds of all cosmic structure, the quantum fluctuations that would eventually grow into galaxies, clusters, and the cosmic web. The pattern of these fluctuations depends critically on the ratio of dark matter to ordinary matter in the early universe. Planck's measurements allowed scientists to determine the composition of the universe with extraordinary precision: 68.3% dark energy, 26.8% dark matter, and just 4.9% ordinary matter. Everything we've ever seen, everything that makes up Earth, the Sun, all visible stars and galaxies, less than 5% of what exists. But the most remarkable discovery involves what happened in the early universe because of dark matter's unique properties. In the first few 100,000 years after the Big Bang, ordinary matter was trapped in an electromagnetic dance with photons, unable to collapse under its own gravity. But dark matter, immune to electromagnetic forces, began collapsing immediately, forming gravitational potential wells. Think of it like this. Dark matter created invisible scaffolding, gravitational wells that ordinary matter eventually fell into once the universe cooled enough for atoms to form. Without this head start, without dark matter creating structure before ordinary matter could, the universe would look fundamentally different. Galaxies would have formed billions of years later, if at all. The cosmic web of structure we observe would not exist. Computer simulations confirm this. When scientists model cosmic evolution without dark matter, using only ordinary matter and gravity, the resulting universe bears no resemblance to what we observe. Galaxies don't form in the right places, at the right times, or in the right numbers. The structure is simply wrong. But when they add dark matter in the precise proportions measured by Planck, matching the rotation curves Vera Rubin observed, matching the gravitational lensing seen in cluster collisions, matching the acoustic oscillations in galaxy surveys, suddenly the simulations produce a universe that looks almost identical to our own. The evidence extends beyond cosmic structure into the realm of individual galaxy formation. Astronomers have discovered ultra-faint dwarf galaxies orbiting the Milky Way, tiny galaxies containing just a few thousand stars, but with masses indicating they're almost entirely made of dark matter, sometimes with ratios exceeding 1,000 to 1. These galaxies are dark matter with just a sprinkle of ordinary matter, like finding a cloud you can almost touch. They exist at the very edge of detectability, visible only because of those few thousand stars embedded in massive dark matter halos. And here's what makes them so important. Their existence was predicted by dark matter simulations before they were discovered. The theory said these ultra-faint galaxies should exist, orbiting larger galaxies in specific numbers and distributions. When astronomers looked carefully enough, there they were, exactly where the simulations predicted. The evidence extends beyond what we can see into the realm of what we cannot see. Dark matter may be influencing the very fabric of space-time in ways we're only beginning to detect. So, what is dark matter actually? What could possibly explain all these observations while remaining invisible and intangible? The leading theory suggests dark matter consists of WIMPs, weakly interacting massive particles. These are hypothetical particles that interact only through gravity and possibly the weak nuclear force, one of the 4 fundamental forces of nature. They don't interact with electromagnetic radiation, which is why they're invisible. They don't interact with ordinary matter through any force except gravity, which is why they pass through everything. According to calculations by physicists at CERN and laboratories around the world, WIMPs should have masses somewhere between 10 and 1,000 times the mass of a proton. They should be moving through space at velocities of a few hundred kilometers per second left over from the Big Bang. And they should be everywhere. Right now, as you process these words, approximately 100 billion dark matter particles are streaming through your body every second. They pass through the Earth as if it were empty space, emerging on the other side completely unaffected. Occasionally, perhaps once in a decade for any given particle, one might collide with an atomic nucleus in your body, transferring a tiny amount of energy before continuing its journey. This is why detecting dark matter is so extraordinarily difficult. Scientists have built detectors deep underground, shielded from cosmic rays and radioactive background, filled with ultra-pure materials cooled to near absolute zero, waiting for that rare collision between a WIMP and an atomic nucleus. The most sensitive experiment, Xenon 1T in Italy, uses 3.2 tons of liquid xenon surrounded by photomultiplier tubes that can detect even a single photon of light. After years of operation, accounting for cosmic rays, radioactive contamination, and every other possible source of interference, they've detected nothing conclusive. This forces us to reconsider fundamental assumptions about what dark matter might be. Perhaps WIMPs aren't the answer. Perhaps dark matter consists of axions, hypothetical particles 1 trillion times lighter than electrons, with properties so unusual they barely qualify as matter in any conventional sense. Or perhaps dark matter is primordial black holes, formed in the first fraction of a second after the Big Bang, too small to have been detected, but numerous enough to account for the missing mass. Or perhaps, and this is where the implications become truly profound, dark matter represents a window into physics beyond the standard model, the theoretical framework that describes all known particles and forces. Every major theory attempting to extend the standard model, from supersymmetry to extra dimensions, naturally predicts the existence of particles with properties matching dark matter. What leading physicists at institutions like Caltech, Cambridge, and the Max Planck Institute increasingly believe is that dark matter isn't a single substance, but potentially multiple types of particles forming a dark sector of physics, parallel to, but rarely interacting with our own. There might be dark photons, dark atoms, even dark chemistry occurring all around us in dimensions we cannot perceive. This is where the evidence leads, toward a universe far stranger and more complex than the one we observe. Recent breakthroughs suggest we're entering a new era of dark matter astronomy, one that might finally allow us to see the unseeable. The Vera C. Rubin Observatory, scheduled to begin full operations in 2025, will conduct the largest survey of the night sky ever undertaken, imaging the entire visible sky every few nights for a decade. Its primary mission includes mapping dark matter throughout the universe through gravitational lensing with unprecedented precision. Meanwhile, the European Space Agency's Euclid mission, launched in 2023, is creating the most detailed three-dimensional map of dark matter ever attempted, observing billions of galaxies to trace dark matter's distribution across 10 billion years of cosmic history. But perhaps the most exciting developments are happening in the detection of dark matter's subtle effects on ordinary matter. Scientists at the Ice Cube Neutrino Observatory in Antarctica are searching for the products of dark matter annihilation, the theoretical process where dark matter particles collide and destroy each other, producing neutrinos and other detectable particles. If WIMPs exist, they should occasionally meet and annihilate, creating showers of particles that ice cubes detectors, buried a kilometer beneath Antarctic ice, might observe. Other researchers are examining whether dark matter might interact with atomic nuclei, not through collisions, but through extremely rare quantum processes, creating signals so subtle they require years of data to detect. The upcoming Lux-Zeppelin experiment in South Dakota will be 50 times more sensitive than current detectors, capable of detecting dark matter interactions that occur less than once per year in its entire 10-ton detector. What this means for us extends beyond academic curiosity. Dark matter shapes the cosmic environment that allowed life to emerge. Without it, galaxies would never have formed at the right times and in the right configurations to produce the heavy elements necessary for planets and biology. The ratio of dark matter to ordinary matter, that precise 5-to-1 ratio, appears to be critical. Computer simulations suggest that if dark matter made up significantly more or less of the universe's mass, structure formation would be fundamentally different. Too much dark matter, and galaxies would form too quickly, creating massive black holes that prevent star formation. Too little, and galaxies would never form dense enough to trigger efficient star formation. We exist in what appears to be a precisely balanced universe, and dark matter is one of the weights on the cosmic scales. Here's what keeps physicists awake at night. What if dark matter isn't just passively sitting there, holding galaxies together? What if it's dynamic, evolving, interacting with itself in ways we haven't detected? Recent theoretical work suggests dark matter might form structures on scales far smaller than galaxies, dense clumps, streams, and possibly even dark matter planets or stars, objects held together by dark forces we know nothing about. These structures would be completely invisible, detectable only through their gravitational effects. In 2021, astronomers reported unusual gravitational lensing patterns that couldn't be explained by any known distribution of visible or ordinary dark matter. The patterns suggested the presence of compact, dense structures with masses similar to small asteroids, but made of something that emits no light. What are they? Dark matter clumps, primordial black holes, or something we haven't even theorized yet? The most profound implications emerge when we consider the possibility that dark matter might not be truly dark at all, that it might interact with itself through forces we cannot detect, forming complex structures and dynamics in a parallel realm of existence. Imagine a civilization that could only perceive gravity. They would know ordinary matter exists because of its gravitational effects, but they couldn't see light, feel electromagnetic forces, or observe chemistry. To them, our world would be the dark matter, and their world, the one governed by forces they understand, would be the normal matter. What if we're that civilization? What if dark matter represents not the absence of complexity, but simply complexity in dimensions we cannot access? Some physicists have proposed that dark matter might interact through its own set of forces, creating dark chemistry, dark molecules, perhaps even dark life. The idea sounds like science fiction, but the mathematics suggests it's possible. If dark matter particles interact with each other through forces comparable in strength to electromagnetism, they could form complex structures just as ordinary matter does. We would never see these structures. They would be ghosts in our universe, overlapping with our reality but fundamentally separate from it, interacting with our world only through the universal language of gravity. Could there be dark planets orbiting dark stars? Dark galaxies with their own internal structure invisible to every telescope humanity has ever built? The evidence doesn't rule it out. In fact, certain observations, unexplained gravitational anomalies, unusual dark matter distributions, patterns that don't quite match simple models, might be hinting at exactly this kind of complexity. The ultimate question isn't just what is dark matter, but rather how many universes are layered on top of each other, sharing the same space but interacting only through gravity. Current evidence suggests at least two: our observable universe of electromagnetic matter and the dark matter sector. But there's no fundamental reason the number couldn't be higher. There could be 3, 4, an infinite number of dark sectors, each with its own particles, forces, and structures, all occupying the same cosmic volume, all influencing each other through gravity, but otherwise completely separate. We are blind to 95% of reality. Think about that. Everything science has discovered, everything humanity has learned about the universe, represents less than 5% of what exists. We began with a simple observation. Galaxies rotate too fast. Stars move at speeds that should tear galaxies apart, yet the galaxies remain intact. From this single anomaly emerged evidence of something profound, a component of reality so fundamental, so pervasive, and so important that its absence would render the universe unrecognizable. Dark matter is real. The evidence is overwhelming, convergent, and growing stronger every year. It holds galaxies together, shapes the cosmic web, and created the conditions necessary for stars, planets, and life to emerge. Without it, you wouldn't exist. Without it, the universe would be empty and formless. Yet, we still don't know what it is. The current scientific consensus recognizes dark matter as one of the most important unsolved problems in physics. Every major astronomical survey, every gravitational measurement, every observation of cosmic structure confirms its existence. The debate isn't whether dark matter is real, it's what form it takes and how we might finally detect it directly. Perhaps the next generation of detectors will capture that first unambiguous signal, a dark matter particle colliding with an atomic nucleus in a laboratory deep underground. Perhaps the Vera Rubin Observatory will reveal patterns in gravitational lensing that expose dark matter's true nature. Perhaps a theoretical breakthrough will suddenly make everything clear, the way Einstein's relativity illuminated the true nature of gravity. Or perhaps dark matter represents a mystery that will challenge us for centuries to come. A reminder that the universe is under no obligation to be comprehensible to creatures made of its minority constituent. But here's what we do know. We live in a universe where most of reality is hidden from us, where invisible forces shape everything we see, where the matter we're made of represents a tiny fraction of what exists. We are made of stardust, yes, but we live in a cosmos dominated by ghosts. And those ghosts are everywhere, streaming through your body right now, holding your galaxy together, stretching in vast halos around every structure in the universe, an invisible architecture underlying all of reality. The universe is vast, the mysteries are endless, the journey continues. The detector found something extraordinary. A source called Cygnus X1, emitting X-rays with an intensity and pattern that defied explanation. The source was compact, smaller than Earth, yet it was radiating energy equivalent to 10,000 suns, concentrated into violent flashes and bursts. Astronomer Tom Bolton at the University of Toronto began studying Cygnus X1 in visible light. He discovered that the X-ray source was orbiting a blue supergiant star called HDE 22686, completing one orbit every 5.6 days. By measuring the orbital motion, Bolton calculated the mass of the invisible companion. The result shocked him. At least 10 times the mass of the Sun, compressed into a region far smaller than any known star. Here's why this was revolutionary. Physicists already knew that when massive stars die, they can collapse into neutron stars, objects so dense that a teaspoon weighs 1 billion tons. But neutron stars have a mass limit. Above approximately 3 solar masses, nothing can stop the collapse. No force in physics is strong enough to resist the crush of gravity. Cygnus X1 was 3 times beyond that limit. The only explanation was that Bolton had found the first confirmed black hole, a collapsed star where gravity had won absolutely, compressing matter past every barrier, through every quantum state, until it punched through space-time itself. But how do you observe something that emits no light? The answer revealed itself in the X-rays. As the black hole's gravity pulled gas from its companion star, the gas spiraled inward, forming an accretion disk, a swirling maelstrom of matter orbiting the black hole. As the gas spiraled closer to the event horizon, tidal forces and friction heated it to millions of degrees, hot enough to emit X-rays. The black hole itself remained invisible, but its feeding process lit up the surrounding space like a cosmic beacon. Astronomers found more. Within a few years, they'd identified dozens of binary systems where invisible, compact objects accreted matter from companion stars, each system broadcasting the signature of extreme gravity at work. Every case above 3 solar masses pointed to the same conclusion: black holes are real, numerous, and actively shaping the cosmos. But the evidence forces us to confront an uncomfortable possibility. Black holes aren't rare cosmic curiosities. They're fundamental components of galactic evolution, present at the heart of nearly every galaxy, including our own. If black holes exist, they should leave unmistakable signatures in their surroundings, effects so extreme that nothing else in physics could produce them. Scientists discovered the first signature in the motion of stars near the galactic center. In 1995, Andrea Ghez at UCLA and Reinhard Genzel at the Max Planck Institute began a decades-long campaign to track individual stars orbiting the center of the Milky Way. Using adaptive optics to compensate for atmospheric distortion, they followed stars for years, measuring their positions with extraordinary precision. One star, designated S2, completed an entire orbit in just 16 years, moving at speeds up to 7,650 kilometers per second, nearly 3% the speed of light. By tracking S2's elliptical orbit, Ghez and Genzel calculated the mass of the object it was orbiting, 4.1 million times the mass of the Sun, concentrated in a region smaller than Mercury's orbit around the Sun. No cluster of stars could be that compact without collapsing. No cluster of neutron stars or stellar mass black holes could avoid merging. The only possible explanation was a supermassive black hole, Sagittarius A star, the gravitational anchor of our entire galaxy. In 2018, astronomers observed S2 at its closest approach to Sagittarius A star, just 120 times the distance between Earth and Sun. At that distance, traveling at nearly 8,000 kilometers per second, general relativity predicts that time should slow down and light should redshift due to the extreme gravitational field. The observations matched Einstein's predictions perfectly. But this represents just one piece of a much larger puzzle. If supermassive black holes exist at the center of our galaxy, they should exist in other galaxies too. They do. Nearly every large galaxy ever observed contains a supermassive black hole at its core, with masses ranging from millions to billions of solar masses. The relationship isn't random. The mass of the central black hole correlates precisely with the mass of the galaxy's bulge, suggesting an intimate connection between black hole growth and galaxy formation. But the most stunning evidence came from an international collaboration spanning the entire planet. In April 2019, the Event Horizon Telescope, a network of radio telescopes spread across the Earth, from Hawaii to Antarctica to Europe, released the first direct image of a black hole's event horizon. The target was M87, the supermassive black hole at the center of the galaxy Messier 87, located 55 million light-years away. This black hole contains 6.5 billion times the Sun's mass, with an event horizon 38 billion kilometers across, larger than our entire solar system. The image showed exactly what Einstein's equations predicted: a dark shadow surrounded by a bright ring of photons orbiting at the edge of the event horizon. The shadow's size, shape, and the distribution of light matched general relativity's predictions with remarkable precision. For the first time in history, humanity had seen the silhouette of a black hole. the shadow cast by the absence of space-time itself. But this represents just one piece of a much larger puzzle hidden in the most violent events the universe can produce. On September 14, 2015, at 09:50:45 UTC, two detectors in Louisiana and Washington state registered a signal lasting just 0.2 of a second. That brief ripple, traveling through space-time itself, carried information about an event that occurred 1.3 billion years ago. Two black holes, 29 and 36 times the mass of the Sun, had spiraled toward each other for millions of years, orbiting faster and faster as they drew closer. In the final moments, they were circling each other hundreds of times per second, creating ripples in space-time, gravitational waves, that propagated outward at the speed of light. When they merged, the collision converted 3 solar masses of material into pure energy, released in a fraction of a second. For that brief instant, the merger emitted 50 times more power than all the stars in the observable universe combined. LIGO, the Laser Interferometer Gravitational Wave Observatory, detected the waves as they passed through Earth, stretching and compressing space by less than 1,000th the diameter of a proton. This impossibly tiny distortion confirmed Einstein's century-old prediction: massive objects in motion create ripples in space-time itself. But the most remarkable discovery involves what gravitational waves reveal about black hole mergers. In the final milliseconds before collision, the black holes orbit each other at velocities approaching 60% the speed of light. At these speeds, frame-dragging effects become extreme. The spinning black holes literally drag space-time around them in swirling vortices. The gravitational wave signal encodes information about the mass, spin, and final merged state of the black holes. LIGO, the Laser Interferometer Gravitational Wave Observatory, detected the waves as they passed through Earth, stretching and compressing space by less than 1,000th the diameter of a proton. This impossibly tiny distortion confirmed Einstein's century-old prediction: massive objects in motion create ripples in space-time itself. But the most remarkable discovery involves what gravitational waves reveal about black hole mergers. In the final milliseconds before collision, the black holes orbit each other at velocities approaching 60% the speed of light. At these speeds, frame-dragging effects become extreme. The spinning black holes literally drag space-time around them in swirling vortices. The gravitational wave signal encodes information about the mass, spin, and final merged state of the black holes. Since that first detection, LIGO and its European counterpart Virgo have observed over 90 black hole mergers. Each one provides a glimpse into physics at the absolute extremes, where gravity is so strong that it dominates all other forces, where space-time bends into knots, where velocities approach light speed. The mergers revealed something unexpected. Black holes come in a wider variety than theory predicted. Some mergers involve black holes with masses that stellar evolution models say shouldn't exist. Some show evidence of rapidly spinning black holes, suggesting they formed through multiple merger events. Some occurred in regions where we didn't expect to find black holes at all. And in one case, LIGO detected a merger between a black hole and a neutron star, the moment when a black hole consumed another collapsed star, adding its mass to its own and sending gravitational waves rippling through the cosmos. But perhaps the most disturbing evidence comes from what happens to matter as it approaches the event horizon. Imagine falling toward a black hole. As you get closer, tidal forces, the difference in gravitational pull between your head and feet, become extreme. These forces stretch you along the radial direction while compressing you perpendicular to it, a process physicists call spaghettification. For a stellar mass black hole, spaghettification tears you apart long before you reach the event horizon. But for a supermassive black hole, the event horizon is so large that tidal forces at the boundary are relatively gentle. You could cross it intact, unaware that you'd passed the point of no return. The evidence extends beyond direct observation into the realm of cosmic archaeology, the study of how black holes have shaped the universe throughout cosmic history. So, what happens inside a black hole? What exists beyond the event horizon, in regions where no information can ever return? According to general relativity, once you cross the event horizon, all paths lead inward. The singularity isn't a place in space, it's a moment in your future, as inevitable as next Tuesday. You can no more avoid reaching it than you can avoid reaching tomorrow. The mathematics predicts that at the singularity, space-time curvature becomes infinite, density becomes infinite. The equations that describe physics break down completely. This is where general relativity admits defeat, where the theory says, I don't know what happens here. So what happens inside a black hole? What exists beyond the event horizon, in regions where no information can ever return? According to general relativity, once you cross the event horizon, all paths lead inward. The singularity isn't a place in space, it's a moment in your future, as inevitable as next Tuesday. You can no more avoid reaching it than you can avoid reaching tomorrow. The mathematics predicts that at the singularity, space-time curvature becomes infinite, density becomes infinite. The equations that describe physics break down completely. This is where general relativity admits defeat, where the theory says, I don't know what happens here. This forces us to reconsider fundamental assumptions about the nature of reality itself. In 1974, Stephen Hawking made a discovery that revolutionized black hole physics. He calculated that quantum effects near the event horizon should cause black holes to emit radiation, now called Hawking radiation. The mechanism is subtle. Quantum fluctuations create virtual particle-antiparticle pairs near the horizon. Occasionally, one particle escapes, while its partner falls into the black hole, carrying negative energy. To an outside observer, it appears that the black hole is radiating. The shocking part? This radiation causes black holes to lose mass. Very slowly, over incomprehensibly long timescales, black holes evaporate. A stellar mass black hole would take 10 to the 67 years to evaporate, far longer than the current age of the universe. But the principle is revolutionary. Black holes aren't eternal. Given enough time, they disappear completely. This creates a profound paradox. Information cannot be destroyed in quantum mechanics. It's a fundamental principle. But if a black hole evaporates completely, what happens to the information about everything that fell in? The books, the people, the patterns and structures? Where does that information go? This is the black hole information paradox, and it remains one of the deepest unsolved problems in theoretical physics. Some physicists, including Hawking himself in his later years, suggested that information is encoded in the Hawking radiation through quantum correlations so subtle we don't yet understand them. Others propose that information is preserved at the event horizon in a holographic encoding, where all the information about a three-dimensional volume is stored on its two-dimensional surface. What leading physicists at institutions like Princeton's Institute for Advanced Study, Cambridge, and Caltech increasingly believe is that black holes represent laboratories for quantum gravity, places where quantum mechanics and general relativity meet, clash, and demand a deeper synthesis. String theory suggests black holes might not contain singularities at all. Instead, the center might be a region of highly excited strings in multiple dimensions, preventing infinite density. Loop quantum gravity proposes that space-time itself has a discrete structure that prevents true singularities from forming. But without observations from inside the event horizon, which are impossible by definition, these ideas remain speculative, mathematical hopes that nature might be kinder than general relativity suggests. Recent breakthroughs suggest we're entering a new era of black hole astronomy that might resolve these mysteries. The Event Horizon Telescope collaboration is now targeting Sagittarius A star, our own galactic center black hole. Because it's much closer than M87, the images should reveal finer details of the space-time structure near the event horizon, potentially showing frame-dragging effects and testing general relativity in extreme conditions. Meanwhile, the LIGO-Virgo-Cagra network is being upgraded to higher sensitivity. By 2025, these detectors should observe black hole mergers occurring anywhere in a volume of space containing millions of galaxies, revealing rare and exotic merger events. But perhaps the most exciting developments involve testing what happens in the most extreme gravitational fields ever observed. In 2020, the Gravity Collaboration observed flares of light orbiting Sagittarius A star at 30% the speed of light, just outside the event horizon. These hotspots in the accretion disk provide a laboratory for testing general relativity at the absolute limits, where gravity is so strong that even light struggles to escape. The observations revealed subtle precession effects. The orbit itself rotates, exactly as Einstein predicted. But future observations with higher resolution might reveal deviations from general relativity, hints that our understanding of gravity needs modification at extreme scales. What this means for us extends beyond testing physics theories. Black holes are engines of cosmic evolution. When supermassive black holes accrete matter rapidly, they produce jets, beams of particles and radiation launched at nearly light speed, extending for millions of light years. These jets inject enormous energy into intergalactic space, heating gas and regulating star formation across entire galaxy clusters. Without black hole feedback, galaxies would form stars too rapidly, converting all their gas into stars within a few billion years. Black holes act as cosmic thermostats, controlling the rate of star formation and thereby determining how galaxies evolve. The ratio between black hole mass and galaxy mass, that surprisingly tight correlation, suggests black holes and galaxies co-evolve, each influencing the other's growth throughout cosmic history. But the most profound implications emerge when we consider the ultimate fate of black holes in the far future of the universe. In a universe dominated by dark energy, where expansion accelerates eternally, black holes might become the last structures to exist, slowly evaporating through Hawking radiation over timescales that dwarf the current age of the universe by factors of 10 to the 60 or more. In that distant future, 10 to the 100 years from now, black holes will evaporate in brilliant final explosions, releasing all their mass as radiation. These explosions might be the last light in an otherwise cold, dark, and empty universe. Here's what keeps physicists awake at night. What if black holes aren't endpoints, but doorways? What if the singularity isn't infinite, but connects to something else? Some theoretical physicists have explored the possibility that black hole singularities might be wormholes, tunnels through spacetime connecting to distant regions of the universe, or even to other universes entirely. Matter falling into a black hole might not be destroyed, but transported elsewhere, preserving information and avoiding the paradox. The mathematics allows it. Einstein's equations contain solutions describing traversable wormholes held open by exotic matter with negative energy density. Whether such matter exists in nature remains unknown, but quantum fields can sometimes exhibit negative energy density, suggesting the possibility might be real. The most profound implications emerge when we consider what happens at the quantum level inside black holes. Theoretical work by physicists like Leonard Susskind suggests that observers falling into a black hole and observers remaining outside might experience fundamentally different realities. To the infalling observer, nothing special happens at the event horizon. They pass through and continue toward the singularity. But to the outside observer, they appear to freeze at the event horizon, their information smeared across the surface through a process called holography. Both perspectives are correct. The same event can have two complete but incompatible descriptions depending on your reference frame. This is complementarity. Reality itself depends on where you're standing. Some physicists have proposed even more radical ideas, that our entire universe might exist inside a black hole in a higher dimensional space. The Big Bang might have been the formation of that black hole, and the cosmic expansion we observe might be the interior evolution of black hole space-time. This sounds absurd, but the mathematics is surprisingly consistent. The geometry inside certain black holes matches the geometry of an expanding universe like ours. We could be living inside a black hole without knowing it. Even more radical, some theories suggest that black holes might give birth to new universes. When matter collapses to the singularity, quantum gravity effects might cause a bounce, creating a new expanding space-time connected to ours only through the black hole interior. Each black hole in our universe might seed a new universe, and our universe might be one of countless offspring from a black hole in a parent cosmos. The ultimate question isn't just what are black holes, but rather what is the relationship between black holes, quantum mechanics, and the fundamental structure of reality? Current evidence suggests that understanding black holes fully will require a complete theory of quantum gravity, a framework that unifies general relativity and quantum mechanics. String theory, loop quantum gravity, and other approaches are working toward this goal, but we're not there yet. What we do know is that black holes force us to confront the limits of our understanding. They're places where our best theories break down, where nature reaches extremes we can barely comprehend, where infinity becomes real and singularities hide secrets we may never fully unravel. We began with a mathematical curiosity, Karl Schwarzschild's solution to Einstein's equations, describing an object so impossible that Einstein himself rejected it. From that abstract beginning emerged evidence of cosmic monsters, places where stars orbit at a fraction of light speed, where space-time itself collapses, where gravity wins absolutely. Black holes are real. The evidence is overwhelming. We've tracked stars orbiting them, photographed their event horizons, detected their mergers through gravitational waves, and measured their influence on entire galaxies. They're not rare curiosities, they're fundamental components of cosmic structure, present in most galaxies, shaping star formation and galactic evolution. Yet we still don't fully understand them. The current scientific consensus recognizes black holes as laboratories for physics at the absolute extremes, places where general relativity and quantum mechanics meet, where information paradoxes challenge our deepest assumptions, where singularities might hide doorways to other universes or might represent the true limits of physical reality. We've learned that nothing can escape from inside the event horizon, but we've also learned that black holes aren't eternal. They evaporate over cosmic timescales. We've learned that they regulate galaxy formation, but we still don't understand how supermassive black holes formed so quickly in the early universe. We've imaged their shadows, but we can't see what lies inside. Perhaps quantum gravity will resolve these mysteries, revealing that singularities are finite structures in extra dimensions. Perhaps future observations will detect subtle deviations from general relativity that point toward deeper truths. But here's what we do know. Black holes represent the most extreme conditions the universe can create. They're places where physics reaches its limits, where our equations fail, where infinity becomes real. They're tears in the fabric of space-time, one-way membranes between the knowable and the unknowable. And they're everywhere, at the center of most galaxies, scattered throughout space as stellar remnants, colliding and merging in events that shake the fabric of reality itself. The universe contains places where time stops, where space collapses, where all paths lead to singularities. These places are not theoretical. They're real, observable, and fundamental to cosmic evolution. The universe is vast, the mysteries are endless, the journey continues. But this represents just one piece of a much larger puzzle hidden in the oldest light in the universe, the cosmic microwave background. When the universe cooled enough for atoms to form, the pressure waves froze into the distribution of matter, creating a characteristic pattern of galaxy clustering with a specific scale, approximately 500 million light-years. Astronomers have measured this pattern in the distribution of galaxies across billions of light-years of space, and it matches theoretical predictions with stunning precision. Here's what makes this evidence so powerful. The pattern we observe requires dark matter to have existed in the early universe at a ratio of approximately 5:1 compared to ordinary matter. 5 parts dark matter, 1 part ordinary matter. This ratio determines the amplitude and wavelength of the acoustic oscillations, and any significant deviation would create a completely different pattern in galaxy distribution. We observe the predicted pattern. The ratio holds. The evidence converges from completely independent measurements made across vastly different scales and cosmic epochs. The bullet cluster represents just one piece of a much larger puzzle. Scientists have now observed dozens of colliding clusters, and every single one tells the same story. The gravitational mass center separates from the visible matter during collisions. But perhaps the most compelling evidence comes from something called baryon acoustic oscillations, pressure waves that rippled through the early universe. In the first 380,000 years after the Big Bang, the universe was a hot, dense plasma. Ordinary matter, protons, neutrons, electrons, everything that would eventually form stars and planets and people, was coupled to photons, creating a fluid that could transmit pressure waves like sound waves through water. Dark matter, unable to interact with photons, remained unaffected by these oscillations. When the clusters collided, their ordinary matter, primarily hot gas glowing in X-rays, interacted and slowed down, creating a shock wave of superheated plasma between the clusters. You can see this glowing cloud in X-ray images, marking where the visible matter piled up during the collision. But gravitational lensing revealed something else entirely. Astronomers mapped the gravitational fields by observing how light from background galaxies was bent and distorted. The gravitational center, the location of most of the mass, wasn't where the hot gas was. It had passed right through the collision point, separating from the ordinary matter by more than 3 million light-years. This is the signature of dark matter. While ordinary matter interacts, collides, and slows down through electromagnetic forces, dark matter passes through everything like a ghost through walls. It's collisionless, interacting only through gravity.
Ongoing research is pursuing dark matter through multiple strategies simultaneously. Direct detection experiments deep underground use tanks of liquid xenon or other materials, waiting for a dark matter particle to collide with an atomic nucleus. The largest current experiment, Lux Zeppelin in South Dakota, uses 7 tons of liquid xenon and can detect collisions producing energies as small as a few keV. These experiments operate deep underground, 1,600 meters below the surface for Lux Zeppelin, to shield against cosmic rays. They cool detectors to near absolute zero to minimize thermal noise. They use the purest materials ever manufactured to eliminate radioactive contamination. And so far, after decades of progressively more sensitive searches, they've found nothing definitive. The lack of signal is ruling out vast swaths of theoretical parameter space, telling us what dark matter isn't, even if we can't yet discover what it is. Recent breakthroughs suggest new search strategies. The ADMX experiment at the University of Washington searches for axions using a high-powered magnet and sensitive radio receivers. If axions exist and pass through a strong magnetic field, they should convert into photons at specific frequencies related to the axion mass. ADMX has been operating for over 2 decades, gradually scanning through possible axion masses. In 2018, they reached sensitivity capable of detecting even pessimistic axion models, entering territory where discovery becomes plausible. Meanwhile, the Fermi Gamma Ray Space Telescope searches for signals of dark matter annihilation in space. When dark matter particles collide, they should annihilate into gamma rays. The center of our galaxy, dwarf satellite galaxies, and galaxy clusters are prime hunting grounds. Some tantalizing hints have emerged: excess gamma rays from the galactic center, unusual signals from dwarf galaxies, but nothing definitive. The challenge is distinguishing dark matter signals from astrophysical backgrounds like pulsars and supernova remnants. What this means for us extends beyond academic curiosity. Understanding dark matter means understanding the universe's structure and evolution. It affects the formation of galaxies, the distribution of matter, the ultimate fate of cosmic expansion. Every question about cosmic history involves dark matter. It also tests the limits of human knowledge. We're forced to study something we cannot see, touch, or directly measure. We must infer its properties from subtle gravitational effects and missing mass in cosmic accounting. This develops new ways of thinking about evidence and inference. We learn to trust mathematics and careful reasoning even when direct observation is impossible. These cognitive tools apply far beyond physics to economics, psychology, any field dealing with invisible influences and indirect evidence. Dark matter reminds us that reality extends beyond human perception. The universe contains more than our senses reveal. Understanding it requires intellectual tools, mathematics, theory, careful reasoning that transcend direct experience.